Hello there and welcome. Today is September 9th, 2025, a lovely Tuesday. And I'm your host, and I'm here to introduce a training article that's been getting some buzz from the archives. Let's dive right in. The title is Crosscoding Through Time, Tracking Emergence and Consolidation of Linguistic Representations through LLM Pretraining. The code is at Time-Lapse Worksive 09.5290. Oh, that's a mouthful. Okay, so let's break this down. Imagine you're watching a baby learn to talk. One day they're just making sounds, and then seemingly overnight they're forming sentences. You know they learned it, but you don't know the exact moment. They understood the concept of a verb or a plural noun. Well, that's the big problem this paper is trying to solve. But for large language models, or COMs, the AI that powers things like tech, they learn incredibly complex grammar during their training. But we don't really understand where or how these specific abilities pop into existence. It's like a black box. We can test them and see they got smarter, but we can't see the little gears turning inside. So how do these researchers peek inside the machine's brain while it's growing up? They use a super clever technique called sparse. Think of it like this. During the LLM's training, the researchers take snapshots, the checkpoints of its internal state at different times. Like a picture at 1 billion tokens of training, another at 4 billion, and one at the very end. The tricky part is that the brain reorganizes itself as it learns, so you can't just compare the snapshots side by side. It's like trying to compare photos of a city taken 50 years apart. The buildings have all changed. What these? Well, is create a shared map, a common reference point that aligns all these different snapshots. This allows them to track a single concept, or feature, over time. And they introduced a new metric called RELIE, which stands for Relative Indirect Effect. Basically, it's a tool to measure how important a specific feature is. For a particular task, like getting grammar right at each stage of training, this lets them see if a feature is just being born, if it's sticking around and staying important, or if it's fading away. So what did they find with this new Time-Lapse camera for the AI's mind? First, they looked at monolingual models, ones trained mostly on English. In the early stages of training, the model learns very simple, low-level things. It's like it's just recognizing specific bits of words, like the subject of hands, or identifying very specific nouns like man or woman. It's real surface level stuff. But as it keeps training, something amazing happens. These simple, tech-and-level detectors start to merge and evolve into much more abstract, high-level grammatical concepts. For instance, instead of just seeing individual plural words, the model develops a feature that understands the general concept of plural nouns, or a feature that detects prepositions. It's building a real understanding of grammar. And this happens even after the model's performance on grammar tests stops improving. The inside is still getting more sophisticated. And we looked at multilingual models like Boom, which is trained on many different languages. And guess what? A very similar process happens, but on a global scale. Early on, the model has separate features for each language. Like it might have one feature to spot the main verb in an English sentence, and a totally different one for French. But as training goes on, the model starts to realize, hey, these languages actually share a lot of the same underlying rules. So it starts to consolidate these separate features into universal, cross-lingual ones. For example, it develops a single feature that can detect relative pronouns, like that, who, qui, or cross English, Spanish, and French. He even developed a feature for the concept of the boss, detecting words like chief, chefaf, and chef across different languages. It's like the AI is becoming a comparative linguist all on its own. It's like trying to understand a sandwich by looking at the bread, then the lettuce, then the ham. This paper gives us the recipe book that shows how they all come together, and also why my sandwich always to learn Portuguese. So why does any of this matter in our daily lives? Well, this research has some really cool applications. Let's look at 3 examples. First, machine translation. By understanding how a model builds a shared sense of grammar across languages, We can create translation tools that are much more accurate and natural. If a model has a strong universal feature for subject-verb agreement, it's far less likely to make silly grammatical mistakes when translating from French to English, because it understands the core principle, not just the surface subtle words. Second, chatbots and dialogue systems. This work could help us build more efficient and smarter chatbot. We know exactly when a model learns a key grammatical concept. We could potentially streamline its training to be faster and cheaper. Also, if a chatbot is consistently making a certain type of error, you could use these tools to look inside to see which feature is weak or underdeveloped, and then figure out how to fix it. It's like diagnostics for enhanced language skills. And third, information extraction and text summarization. To summarize a long article, an AI needs to grasp high-level ideas, not just individual words. This paper shows how models learn abstract concepts like verbal nouns, which are nouns made from verbs like performance from perform. A model with well-developed abstract features can better identify the core actions and ideas in a document, leading to summaries that are more accurate and coherent. So, how does this compare to what we could do before? Previously, researchers often used something called sparse plane loaders, or SACEs. You can think of an SACE as taking a single, high-resolution photograph of the alien's brain at one specific moment. It's useful, but it's just a static snapshot. You can't really compare it to a photo taken earlier, because everything has shifted around. Your used in this paper are fundamentally different. They're not taking a single photo. They're creating time-lapse video by aligning the features across different training stages. They let us watch how a single concept is born and how it evolves. It's a huge leap forward because it allows us to study the dynamics of learning, not just the final result. So the big takeaway here is that we're finally getting the tools to watch how these incredibly complex language models actually learn language from the ground up. They start with simple building blocks, like recognizing parts of words, and gradually build them into sophisticated abstract, and sometimes even universal grammatical concepts. It's a fascinating glimpse into the mind of a machine. That's all the time we have for today. Thanks for tuning in, and I'll catch you next time.